Alright, so today I was thinking to continue working on the stack tool, but this time let's add an extra feature, like it's kind of outside of the stack tool. It's gonna be adding error correction codes. That's usually kind of useful in networking stuff, and from what I understand, with encoding information in images, it's also kind of useful to use some kind of error correction because you are gonna get some compression when you are gonna send images across network. So, it's still kind of useful to have some kind of, being able to correct errors in case they happen, or at least detect them. So for today, I was thinking to go through maybe the intuition of how we get to the Hamming code. Honestly, I mean, I looked a bit into it, how you are supposed to do it, kind of understand it. So I was thinking to maybe explain how we start with something called parity bit, and then how we actually get to the main stuff from the Hamming code. So yeah, let's actually start. So just check. So yeah, let's have a look into this. Like let's take an example, right, of a number like in binary, and we are gonna try to compute some parity bits and then look into Hamming code, or at least step by step we'll get there. So maybe first of all, this would be something that we want to send via network. So this is gonna be. Wait, I would like to draw it white, honestly. So we are gonna send this thing across a network, and maybe we are gonna lose 1 byte or a bit, or maybe I don't know, like something could happen and we get something wrong on the other side, and we would like to at least detect that something went wrong, right? So the easiest way you could do that would be to use another bit, and this bit would represent, let's say this one is called a parity bit, right? So usually you have a parity bit, and this one would count how many bits of one you have in your data. So if you have, in this case, you have 2 and then 3 and then 4, right? So we have 4 1 bits. And the convention usually is that if the number of 1 bits is even, you use a 0, and if the number of 1 bits is odd, you use a 1. But in this case it's 0. But then you might say, okay, but what if you lose 2 bits of 1 and they become zeros? Then it's still correct, right? So it's not that good. It only works sometimes. So we might want to think of some better way of um, doing this stuff. So I guess something else that could be done. So with I guess the parity bit probably is pretty obvious how it works. Yo, hello. It's like a single bit, but we want to be able to correct more errors than just I don't know, my middle mouse button is broken. I'm gonna use space. So let's say we want to correct more errors than one, right? So with Hamming code, I guess there was somewhere here that the error rate, the message length. So okay, let's think how we can try to fix more error than just with one parity bit. So what we could do is, let's say we have the numbers that are powers of 2, like 1, 2, 4, 8, and so on and so forth. So there are quite a few. Well, in binary you would write this as 0, 0, 0, and then 1. Let's just pretend we have 7 zeros here. Then for a 2 it's kind of similar, but it's 1 0 at the end. Then for a 4 it's 1 0 0, and then for the 8 is 1 and then 3 zeros, right? So it's something like this. And what we are gonna do with these numbers is, let's say we want to insert them into our byte string, right, in our bits, and we are gonna use these positions. We are gonna start with an index of 1 because it's gonna make our work easier. But let's say we want to insert these indices to be parity bits, and the other indices are going to be our data bits. So in the end, our number would look something like empty space for this guy. Then we have another empty space for the 2. Then we are going to write stuff from our data. So it's a 0 here. It's our, we can also index them like 1, 2, 3, right? So 3 is our first data. This one is, out of scope at this point. Then we have a 4, which should be another parity bit. So it's index 4. Then we have, again, stuff from our data like 1, 1, 0. So this is 5, 6, and 7. Right? Then we have another parity bit. And then we're going to have the rest of the data. It's going to be, so this is 8, 1, 0, 1, 0, I think. So this is like 9, 10, 11, and 12. Right, so that's how we would build our new message. As you can see now, it's 4 bits longer, so it's larger than it was before. It's 50% larger, so we are gonna need to use more packets, or at least bigger packets, to send the information. But at least now we would have some kind of error proof message, or at least that's what we wish we could do. So let's see if we can actually figure out a way to use these new positions to add some error correction. And the easiest way to do that would be, and this is the part that's, oh, that's kind of cool, would be to do something like, for index 1, let's look at all of the positions from here that have 1 bit in the last position. So what positions are those? Let's color them with green. So would be the first one. Obviously it's the odd numbers, because only odd numbers have a 1 bit here, right? Like that's kind of how it works. So 1, 3, 5, 7, 9, and 11. So these are the positions that have a 1 bit in the last positions, right? And what we want to do now is to count how many bits of 1 do we have. So we have 1, 2, 3, right? So it's an odd number of 1s, so we use a 1, right? So that's how we get the first parity bit. Then how do we get the second one? Well, we are gonna look at the positions that have a 1 in the second to last bit. So those are gonna be, I think it's 2 and 3, right? Then these two we are gonna skip these two. Then we have these two. I think also skip these two, and then these two, right? So you can say that it's 2 of them are gonna have a bit, then 2 of them are not gonna have a bit. I mean, you can also check, right? So if we do something like Python 3, I think I was checking this earlier. If you are trying to print the binary format for 6, you're gonna see that it has a 1 bit here in this position. So 6 is gonna be part of this, but for instance 5 does not have. And you can check all of these numbers and figure out which one is part of each index. Okay, so let's see how many bits of 1 do we have now? So here we don't have any, here we only have 1, and here we have another 1. So we basically have 2 bits. That's even, so it's 0. Cool. Now let's take a look at 4. So 4, okay, you can trust me, these 4 bits, or I guess these 4 positions have a 1 here, so we are gonna take all of them. Then these 4 do not have a 1 there, and then, you know, would be 4 more from here, but it's not important. And if we take a look at these positions, we have 2 bits of 1, so that's even, so it's 0. Nice. Okay, and the last one is the 8th position, so we need to take a look at bits that look like this. So 1 something something something, and those bits are gonna be 8 bits from here. But you know, since we don't have anything else here, it doesn't matter that much. So let's take a look at what we have here. We have 2 bits of 1, so it's gonna also be a 0. Okay, so it's even. That's why it's 0. Okay, that's kind of interesting. So that's how we are able to get these parity bits. But now you might ask, okay, but what can we do with them, right? Like, let's just imagine that we have over the network we sent this entire string. So let's say we sent all of this stuff over the network, and we received something a bit different at the end. So can I just maybe, I was thinking if I can copy paste this thing just to, okay, let me delete that. So let's say we receive something different over the network. So maybe, I don't know, like instead of a 1 here, we have a 0. So let's put a 0 here like that. So let's pretend we have a 0 here, right? And we are going to compute these parity bits again when we receive the message. So obviously that's something we are going to do. And let's take a look at the values this time. So we know that for the 1 bit, we look at these positions, right? And we have 2 1s. So that means that this guy should be a 0, right? So obviously it's wrong. It should be a 0, right? But right now it's a 1 because we have here it's a 0, here it's a 1, here it's a 1. So we have 2 bits of 1, so it's even. That means instead of a 1, we expected to see a 0, so it's wrong. Okay, then let's take a look at the second parity bit. And for the second parity bit, we need to take a look at this stuff, and this stuff, right? So yeah, this is getting skipped. So this one is fine because we have 2 bits of 1, right? So this has the expected value. It's a 0 because the number of 1s is even. Now I guess I took like a really weird example here, but let's see if it actually works because I changed, no, I changed like a data bit. Don't worry about it. Okay, so then let's take a look at another example. So or I guess at the next parity bit. So this one is the third one, and we would expect, or I guess we would check these 4 and 4 from here, but we don't have anything left, so it's only these 4. And in this case we also have only one bit, so we actually expected to see a 0 here, right? Or I guess a 1, and it's a 0, so that's not really right. And then at the end, you know, this is still fine, everything from there is fine. So this would be okay. And we have also the indices of these things. So this is index 1 and this is index 4, right? So what we can do now with these parity bits that were wrong, we could actually add them together. So 1 plus 4, and that gives us 5. And if we check our message, index 5 is actually the bit that's flipped. So that's how we can actually figure out which bit was flipped. We can actually look at the parity bits that are wrong, or we expected them to be different, and add those indices together, and we get the index of the data that is broken. So that's, I mean, when I first figured this out while looking on the Wikipedia stuff and trying to write it down on my own, I was like, holy shit, that's actually kind of cool. And obviously, like, all of these indices were chosen such that this thing happens, right? So I'm not sure if it's a property of or I guess the fact that you only have one in here, but, or I guess, I don't know if the dude did the math first or just took an example and saw this thing and was like, holy shit, that's a good one. But for me, I was looking through the example and I was like, holy shit, that actually works. That's crazy. But the thing is, I'm pretty sure that this only works to find one bit and correct one bit. And I think that's also kind of mentioned here, that because we are going to try to implement Hamming 7.4, that's the easiest one, I would say. And it says somewhere around here, but it can detect and correct single bit errors. So as you can see here, if you have one bit flipped, it's pretty easy to find the location and fix it. Like, we know 5 is wrong, so we have to flip it to a 1. It also says that it can detect double error bits. Not sure. Maybe we can, take an example and see what would happen if we try to correct, if we have 2 bits flipped. And another interesting one is what would happen if one of the parity bits are flipped. So let's try to make that case. I haven't tested it. So let's say this one is flipped. All right, so this would be a 0. This would be a 1, 0, 1, 0. Okay, so when we go over these things, we are gonna notice that, so for the first one, everything is good, right? It has a value of 1, just like we expect. Then for the second one, I think also everything works fine, so it should still be a 0. We have even number of ones. But then for this guy, we are gonna say something like, oh, we expected to have a 0 here, but we have a 1. So obviously this was fine, and this is wrong. Or I guess this is wrong. So we expected a 0, but we have a 1. Then this one is also fine, right? So I would say it's not really addition that you do here, but it's actually some kind of overlap. So what do I mean by that is, if the 5th bit is wrong, then you need all the components that make up 5 be wrong. So 5 is actually, if you write it in binary, is like, well, I mean, sure, it's just addition, but it's kind of interesting to think about it also like this. So if you look at this table, it makes actually a bit things a bit more easier. It's like, so we had parity bit 1 and parity bit 4, as wrong. So I had to scan over this entire thing and find like the intersection between them, or right. So it should be just the intersection that we find. So here you can see that only parity bit 1 and parity bit 4 are being wrong. Obviously this one is also happening, but in our message we don't include 13, so we are good. So you can see that only these two are wrong. It kind of makes it easier to use this kind of format, but I think it's also fine how we did it. But yeah, I mean, in fact, it's just addition, because if we take a look here, we have only parity bit 4 wrong. So 4 is just 4, right? So we know that index 4 is wrong. But we don't even care about it because it's just parity bit. You know, we don't care about parity bit. Okay, so that's pretty straightforward, I would say. So if a parity bit is wrong, then it's not that big of a deal. But what I'm also curious about is what if we have two bits that are wrong? Because maybe that's going to be more interesting. So this could be a 0 and this would be a 0 as well. So obviously we would say that this is wrong because that's that. Then this is also wrong. What else? Here, this one, pretty funny. This one is gonna be right because we have an even number of ones, which is, you know, 0 ones before we had 2. Okay, and then this one is gonna be right as well. So this thing kind of tells us that, you know, 1 plus 2 is 3. So this kind of tells us that this one is wrong, but that's not actually true. So yeah, I'm actually curious how this thing solves, or at least how can you detect that you have a double bit error. No idea. Whatever, we can ignore this case. Let's just say that in a, you know, in a perfect universe you won't have more than 1 bit errors. Still haven't gotten into how you can detect, because you cannot really fix 2-bit errors from what I understand here. You can just detect them. Okay, so maybe it's used differently. Maybe it's not used like this if you want to detect double bit errors. But anyway, so I guess this would be kind of not that complicated to implement. Although my problem with implementing this thing in C is that it would be kind of annoying to have to get a number and then put all of these parity bits inside of it. It's, you know, not ideal. Let's just say that. It's a bunch of computing all of these numbers. I mean, we could try. It's gonna take a while for me to figure out the indices in code. So I guess that's the main reason why they actually came up with some matrix stuff, which I, you know, I was looking into this and I was like, what the fuck is this? Like, how, where did this thing spawn from? It's like, doesn't make any sense. But actually, you know, I mean, I forgot all the math notations from like 5 years ago when I was actually doing math in school. So yeah. And I guess the problem when I was looking into this and I was like, what the fuck is going on, was that I was starting with G, which G is a bit more complicated, and I think H is the easier one. So for H, I guess let's first take a look at what these numbers mean. I guess that's a bit more intuitive. So what is having 7 for, right? So let's say we have only 4 bits of data, so 1 0 1 0. This would be the 4, right? But what is the 7? Well, if you want to do the same thing like we did here, but with 4 bits, you would need uh, 3 bits of 3 parity bits, right? So then you have the 1, then you have the another parity bit, and then you have 3 more data bits. So 0 1 0. So this would be our new data that we send, and obviously there is a unused thing here. Okay, so this would be our block. So you can see that we have 4 bits and we need 7 bits to actually encode the Hamming code. So that's where the 7 and the 4 come from. Okay, and I guess the other thing here is, not sure where they mention what N and K was, because those are also fine. Oh, here. So N is the amount that we need to send a message. Then K is the number of bits that we have, and I think D is just the difference between them, like 3, obviously. Okay, so when we want to compute H, it's called parity check matrix, and this guy is just used to if you multiply two matrices, hopefully you know how to multiply two matrices. That's kind of not what we are gonna learn here, but if you take a look at the H matrix, let's see how do they explain it in an easier way, because okay, let's just take the intuition approach, right? So we want to have a matrix, and in this matrix you want to put columns that have a length of 3, or like a size of 3, because that's 7 minus 4, right? And we want to use ones and zeros in here, and we also want to have, so this is gonna be a 7 by 3, so 7 columns and 3 rows. That's how you, I think it's 3 rows and 7 columns. I'm in math, 7 by 3. I don't know the dimensions. So what do we want to put in here is all the permutations of ones and zeros, right? So we are gonna put 1 1. Actually, let's start with the easiest one. So 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, and 1 1 1. And I mean 0 0 0 is gonna be missing because we don't like those things, but this is gonna be our H matrix. So it actually doesn't really matter the order that you put these things in. You can still get the same encoding. It's just that these bits are gonna have a different order in the final message. So depending on the order that you put your columns in, you are gonna have a different order for these parity bits. But the algorithm works exactly the same. And I guess the convention that they explain here to maybe make things a bit easier is to put this column, and this column at the end. And what that's gonna do, or is it, yeah, I guess they are at the end, right? So that's usually called the I matrix, right? Because it's one on the diagonals. Don't know really the reason why it's called I, but whatever. And also another interesting thing is putting the zeros in a diagonal like this. I guess it's just OCD, right? So the author probably had OCD and was like, okay, let's sort them like this and like this. So it's not really that important, the order of them. It's just that you have to remember the same order and use it on the decoder as well. So again, it's just when you work with bits, usually what operations you apply don't really matter that much, you know, as long as they make sense. Oh, thank you. But what's more important is to apply them both on the encoding and on the decoding. So that's kind of the idea here. And I mean, obviously we are going to use this one because this one is the one that showed on Wikipedia, right? And then for the G matrix, once you have the H matrix, it's pretty easy to compute it. So let's say we order our columns the same as they do here. So 1 1 0 1 0 1 0 1 1, then all ones, and then is the diagonal matrix, right, like this. So this is going to be our H, right? And for the G matrix, this one has a dimension of 4 by 7, right? And in this one, the first half of it, we are just going to start with a diagonal, so it's all going to be ones. Okay, I mean, you know, don't mind the spelling. Perfect. So it's all ones on the diagonals, and then the second half of this matrix is gonna be we are gonna take the lines from here and we are gonna make them columns. So 1 1 0 1, so that's the first line, then the second line 1 0 1 1, and then the last line, right? So that's kind of what we are supposed to do there, right? And that's gonna give us H and G matrices. So what can we use these things for? I guess that's, you know, a good question. Let's take our example. So let's take our example from here with 1010 1010. Let's actually compute the parity bits manually first. So we know that we need parity bit here, and parity bit here. So as usual, first one is this. So it's Z. Let me use green. So it's 0. Then the second one is this one and this one. So it's also 0. Interesting. And the last one is 1. Okay, so that's our manual, doing things manually. But what if we do something like 1010 multiplied with G? I think that's how they did it here. And yeah, I mean, matrix multiplication, hate those things, but let's try to do it. So what you can notice on the first half is that since this is the I matrix, this multiplied with this, and this is going to be the same. So we are going to get, in the first half, we are going to have 1 0 1 0, and then we are going to have some extra stuff here, right? So hopefully it makes sense that if you multiply this row with this column, you get the first item, then the second item. So it's like how multiplying with I works. But now is the more interesting stuff. We multiply this one with this one. So here we are gonna get this multiplied with this multiplied with 0, this multiplied with 1, this multiplied with 0. So we have, let's color it in green. So we have a 1. Then we have this one with this one. This is gonna give us 1 with 1. It's 1. Then it's another 1 from here. So it would be 2. But let's write it as 2. But since we are, in base 2, it's actually 0. So let's just do that. So it becomes 0. And then for the last one, we also have a 1 though. I was thinking it's gonna be these bits, but actually no. Curious. 1101. Even have the same things. Kind of strange. I was expecting them to be the same numbers. Maybe I did something wrong here, although I don't think so. So I took this one, then skipped these two, and then these two. So that's 0. That's fine. Oh yeah, I did something wrong for the first one. The first one should be a 1 because it's this one, this one, this one, and this one. So it's a 1. My bad. So you can actually see that when we did this thing manually, we got 101, and when we did it with the matrix, we also got 101. So basically, this matrix computes the parity bits, and as I said, because of the order of these zeros here or whatever, you actually get them at the end. So if we used another order in the H matrix, we would have probably gotten them, I don't know, at the beginning or in the middle, something like that. But since we use this order, we get them at the end. So that's the main reason why we want, the OCD order in H and J and G. So again, if you now multiply your message with the G matrix, you get the error corrected code inside of your message. So hopefully, that makes sense. And the last thing, I haven't looked into it, honestly, it's an additional parity bit. So from what I understand, the additional parity bit is like, okay, let's take a look at the entire message, and we have 1, 2, 3, 4. So the additional parity bit would be 0, but I don't think we are gonna care about it right now. Like, we are gonna keep an extra bit as a question mark because we don't care about it, but what's important is this one. So why not? Let's just try to implement something really quick and dirty in C for this thing. So as usual, we'll start with stdioh and the hello world. So yeah, I wish C worked like that. Okay, let's do printf hello world. I need that new line. Okay, perfect. So return 0, and let's use Clang on this thing. Perfect. So we have hello world. Okay. Well, I guess first thing would be to just define these two matrices. So H. Well, actually, we only need G. H is not even needed. Like, H is only needed for figuring out G. Right? So yeah. Okay, fair enough. So then let's just define G, and I think I want to do, can I do const assign char G, and this is gonna be a 3, no, it's 4 by 7, right? 4 rows, 7 columns. I think that's how we are gonna do that. So for G we have, I'm curious, does Copilot know what I'm about to do here? It has no idea. Okay, perfect. So, AI is not gonna take our jobs. Let's chill about it. So, do I want to use, I guess I want to use ones. 0, 0, and then 1, 1, 0. Obviously, we could make this thing like insane and use integer instead of a char 7 here, but would that work? Would that actually work? I guess I want to switch this and use columns. If I want to do that, that would be kind of cool, but at the same time, I don't know. Yeah, let's not worry. Let's do it the easy way, and if we have time or something, we are gonna try to do some dumb stuff, but no. Okay, so then we have 1, 0, 1, then we have 1 here, 0, 1, 1, perfect. Okay, so the last column is just, or I guess last row is just ones, perfect. So this is gonna be our G stuff. Let's say we want a message. I mean, message is gonna be hello world. So pointer message is equal to hello world. Maybe I also want to make it unsigned char, just because you're gonna read some data from a file probably or something, so yeah. Okay, and then size t, message length is just strlen of message. I mean, we can just cast it. You're probably also gonna get a message length from the reading function, so that's fine. Okay, so we have the message length. As we already know, we can encode only 4 bits, so only a nibble, if you will. So let's try to build like an encoding function, static void encode. I guess it's not Huffman. It's funny, it's Hamming. I don't know why I was thinking Huffman. I think it's because, do not be confused with Huffman code. Let's look into Huffman code after. I mean, I already did something with Huffman code a while back. It was that auto-completion algorithm, but maybe we can revisit that. So Hamming code, Hamming encode. So it's going to be hard coded for 7.4. It's not really important. So let's have unsigned char pointer message. Maybe also make it const. Size the message length, and I think I want unsigned char. I think I want this function to allocate stuff, or do I? Let's say we have output and size t pointer output length. So this is going to be our encode function, and we are going to use a strategy similar to what we did with DCT in the stack tool. So we are going to have something like bit index is equal to 0, size t byte index is equal to 0. Well, first let's allocate the memory. Okay, so output length, and as I said, I'm gonna keep one bit as unused because I don't want to think about 7 divided by 8 and stuff. Let's not worry about stuff like that. So it's gonna be, the output length is gonna be message length times 2, right? So we basically turn 4 bits into a byte, so 1 byte into 2 bytes. Hopefully it makes sense. Okay, and output is gonna be malloc output length times size of unsigned char. Okay, obviously if star output is equal to null, we are just gonna exit and exit failure. Okay, so now let's take a look at how we are gonna iterate this thing. So I want to iterate it like I want to go from 0 probably to message length, or maybe from 0 to output length. Let's do, I don't think we need these. I think we want to do up until output length probably. Like we could also do message length and then do 2 times. I think that's maybe gonna be easier, message length. So we are gonna have I is gonna represent the index from the message. So we are gonna do something like unsigned char byte is message at I, and then we are gonna split it into 2. So we are gonna have unsigned char lower is byte and 0 b 1 2 3 4 like this. So this is gonna be the lower part of the byte, and then we are gonna have the high part of the byte, which is gonna be byte shifted by 4 and then ended by this. All right, so this is gonna be the high part of the byte. Okay, and then size t output, let's say lower index is gonna be I times 2. Size t high index is gonna be I times 2 plus 1. Although I kind of want to put high first. Right, so it's I times 2 and I times 2 plus 1 for the lower index, just so we have them in order. Okay, and for now let's just test writing into output. So output at high index is equal to high, and output at lower index is equal to lower. And I also want to do Hamming decode. So this is going to take as input a message that's encoded, output. The output length is actually divided by 2 this time, right? We allocate the output, and I guess this time let's iterate on output length. That's the smallest one, right? We need to take high index and low index, and we are gonna say high is message at high index, and this one is message at low index. And obviously output at I is actually high shifted by 4 or actually not really that. I mean, we should do the encoding first and then test it. So let's maybe have a function like static void Hamming helper encode, and this one is going to take as an input a single byte, but let's call it nibble. So it's going to be the lower part of a byte, and we want to output a byte, right? So we want to write into byte. So I'm gonna do something like Hamming helper encode. The nibble is gonna be high, and the output is output at high index, right? And we have the same but with lower and lower index. So that should be the encoding, but let's actually implement it. So I'm gonna do unsigned char. Do they call it somehow here? I think it's called X or something. A. So A is gonna be equal, is gonna be a 4, and it's gonna be equal to, let's think, nibble, we shift this nibble by 3, and we end with 0b. We end with 1. Let's not worry about it that much. Then we have shifted by 2, then we have shifted by 1, and we have shifted by 0, and end with 1. Do I have to put parentheses? I think I do. I'm not sure, because yeah, we want thank you. So yeah, we want I think we want parentheses because I don't know the order of the operations for shifting and ending, so that's something. Okay, so we want now to multiply this with this, so maybe we want a function for matrix multiplication. Void math mul. So let's say we have something like unsigned char star star a, size t a width, size t a height, and then unsigned char pointer b, but it's not really matmul, it's vec matmul or something. It's multiplying a vector with a matrix. So this one is gonna be the vector and size t v, so it's width, it should be like the height, but let's think. So we have this one is 4 and that one is 4 by 7, so this one is 4 by 1. I mean, you cannot really, it has to be 1 by 4, but right, because we multiplied this with this, so it's VH. I mean, it's actually, this one should be first. Let's move it first. It's gonna make more sense. So we are trying to multiply a vector with that, and we need unsigned char pointer out. So this is gonna be the output, and the output is gonna have a size of width. So this is the output vector. Okay, let me just put it on a second line. Okay, so let's see how we do this matrix multiplication. If we think about it, we want to iterate the largest one first. So for size t, I guess the width. So for w is equal to 0, w is less than a width, w plus plus, or I mean, this is the column, let's call it column. Right. Then we are gonna have something like a sum is 0, and then obviously out at column is sum. I mean, is that really, I mean, maybe instead of column, I'm just gonna call it I. So out at index I is sum, and here we need another for loop over the height. And obviously the vector height needs to be equal, so maybe we can just assert that v, or I don't know, like if AH is different than VH, then we just assert 0 and size does not match. So we already know that we are not going to have that case, so VH needs to be equal to AH. So let's do size t j is equal to 0, j is less than VH, doesn't really matter which one we use, and here we need to increment our sum. So sum is going to be increased by Vj times Aj. Right. So I think that's the idea. Like here you can pretend that this is a matrix with 0, right? So that's going to give us the sum. I mean, vec matrix multiplication is just it's like matrix multiplication but with a column. So yeah, so this is going to be, let's make it an 8. Although even 7, it's fine, 7. So we are gonna get that in there, and then let's do vec mat multiplication. So the vector is gonna be A, size is 4, then we have the matrix G, width is also 4, right? And height is 7. Did I think I put them the other way. So width is 7 and this is 4. And the output should be X. Not sure what it doesn't like. Okay, unsigned char pointer. This could be const. Sure, fair enough. So this one could be const. This one could be const. I would rather put, yeah, the height first and the width second because it's gonna make it look prettier. Okay, OCD. Let's move this one here. Okay, so it still contains unsigned char pointer. And it wants const. Perfect. So I mean, we still get the multiplication done into X, and we want to write that into the byte. So we can do that by doing something like, so X0 is gonna get shifted by, we are gonna end, actually we have to modulo 2, and if we modulo 2, I mean, we could also end with 1, why not? And then we shift by 7. And then we have to OR. And then, you know, we kind of do the same thing, but here it's gonna be a 2. Actually, let's do a for loop where size the I is equal to 0, I is less than 8, I plus plus. We're basically gonna do byte is equal to byte or this thing. And as you might guess, this one should be I. Oh, so it's like this. So the index here should be I, and here we should do 8 minus I minus 1. All right, so that's gonna give us a byte, and this is gonna encode our Hamming stuff. So this is gonna probably work. And how about the decoding function? So let's take a look at the helper then code. Wait. Wait. So the helper decode should take as input a single byte, and it should output a nibble. Right, and for now let's just ignore the entire checking. We're gonna do that later, but for now let's just say that the nibble is just gonna be a byte shifted by 4 and end it with 0 0 0 1 1 1. So maybe a to do actually check for errors, but for now let's just see like printing. So Hamming decode, we get the high nibble, the low nibble, or I guess the bytes, and we want to build the nibble. So let's have something like unsigned char. So these are like bytes, high byte, lower byte. So then we can have I is equal to 0, and then we just call this function, the decode function. So here, let's see, we have hi byte, and we send in hi. Then we do the same, but for lower. Okay, and then we can have something like unsigned char byte is equal to, and we need to shift them. So high shifted by 4. Hopefully shifting puts zeros, and then lower. But just to make sure, I think I want to end high with 0B00111, and I also want to end lower with 0B00111. So this is probably going to give us the byte, and we want to write the byte into output. So output at index I, right? Index I iterates over the output is equal to byte. What? I have to reference it, yeah. Okay, so that's how we get that. So let's try to actually encode these things. So having encode takes the message length, and let's have something like unsigned char pointer output is equal to null, size the output length is equal to 0. Let's send in the output and output length, the address, both of them, and let's print f each individual thing. So size the I, or maybe even encoded in encoded message, new length, and then we print the new length, because I'm curious if it's gonna be double. I mean, it is gonna be double because we multiplied by 2, but printf. Here I'm gonna say message byte, and I'm pretty sure you can see printf binary. Can you printf by? Okay, that's a Python thing, I would say then. Printf format binary. Like, can you not print a binary? Percentage %b, that would be, yeah, whatever, you cannot. So let's do %d for the byte. Same. Come on, like, I know you can printf like yeah, I usually like to live stream like at this kind of hour. Like I started an hour ago, I think, or an hour and like 10 minutes or something. So yeah, I mean, can also change that if but kind of like these hours. Message byte. So this would be message at index I. Just curious if it's actually gonna work. Let's see. I forgot to index something. So hemming encode. Let's do some printfs here. %d. Interesting how I actually got printfs there. Wait, what the fuck? Okay, somehow I saw this thing before. Like, it's not the first time I see it executing something twice because of some kind of probably Stack Overflow. It's running main twice. That's crazy. Um, yeah, that's kind of interesting. It does some kind of overflow, right? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Am I not allocating this one properly? Fuck. I mean, this one is decode, so some problem with encoding, I guess. High index, so we have message length, message length times 2 plus 1. So is this not right? So if it's 0, it's 0 and 1. If it's 1, it's 2 and 3. I mean, it should be good. Let me just remove that, see if... Okay, dude, what the fuck? So having encode, I'm not even calling this stuff. What? Okay, let's just I don't know, printf the byte. Okay, what the fuck? This this stuff, man. So we are just iterating over I, we are just reading the message. The fuck? Just printfing stuff. Man, sometimes C is insane. It was printfing 0, that's crazy. Maybe this thing actually doesn't work and I have to hard code it to 12. Nope. I mean, it was working obviously, but come on. So this for loop seems to be like a problem. It's not even the problem, what the fuck? Dude, this shit's crazy. Okay, maybe just call Valgrind on it and see what's wrong. Minus G on it. C-bug, question mark. So like we're just multiplying this thing by 2. That's all this function does. That's crazy. Yeah, like this is the stuff that I really hate about C. Stuff like that. Then like what? Just calling this function. I don't even know what's wrong here. We're just multiplying message length by 2. And just delete all of this stuff. No way. No, I deleted that and it worked. So it's something to do with what? Wait, what? What the fuck? Like literally there's nothing changed and now it works. The fuck? I mean there's no for loop here. But no, yeah, I was doing I++ and everything right? Oh my, yeah, obviously. I was not doing I less than. I mean, no, sometimes it's kind of funny. I was like, what the fuck is going on? Okay. So let's see if so message byte is kind of 0, but I guess I'm not printing the right thing. I'm printing the message instead of the output, and that, you know, that made sense. But here, why is it all zeros now? Oh, and that's a curious thing. Okay, so let's print f %d. So this would be lower, high and lower. For a, I mean, you know, those are decent looking numbers, and we are writing them in here. Now I'm curious maybe to look into x, print f, x is equal to %d. If I is less than 7. Why is it segmentation fault? Am I not writing into? I do, and it's also allocated. Let's make it 8 just. Wait, now where is it segfaulting? I guess, on 23. It multiplies the V and A matrix, makes sense, and then 35. It was called, so I guess I have G there, I have A here, it's 4 by 7. So if I index with, so A width is 7 and A height is 4. Isn't this how you're supposed to do it? Interesting. So VJ 0, 1, 2, 3. J goes from 0 to 4. So that's, this one's good. A at J and I is like 0, 0, 3, 0 and stuff. So that should be good. Is the percentage D. So V is 0 and then it died for the A matrix, which is just G. What? It's unsigned char. Int F. Maybe I need to print F, I, and J as well just to see them. But if I or J were wrong, then I would assume not. Okay, it's probably gonna be fine. Let's just see them. 0, 0. You know, well, instead of A, I'm just gonna use G. I don't really care. So we're just gonna use G. All right. So we still get some stuff. I don't know why this conversion doesn't work. I'm gonna look into it, but let's just use G for now. Yeah, here we are just getting the value, high and lower. Where do I use some extra printfs? So high and lower, I mean, those are some normal numbers. So encode. So here I was curious what the value of byte is. Printf percentage %d star byte. Maybe even here. So it starts with 0 and then 74. So we have some values inside of those bytes. But why is it not getting written in that? Okay, char byte, whatever. Let's put here byte, and this one is equal to byte. Let's just do A. I mean, byte is not needed anymore, so maybe I can just reuse it. Maybe it's how the thing gets dereferenced here. I don't know. Shit. Okay, let's check again. It's still 0, what the fuck? Yeah, we have some values in there, but why is it just showing us 0 here? Because we are literally allocating memory and then writing in that memory, so let's check with Valgrind again. Maybe we have some memory errors. No, just freeze. Let me just double check the index. So high index. Yeah, whatever. So it's like 20, 22, like it looks fine. I don't know why the fuck we only have 74 in here. Am I not allocating this properly? It's output length times the number of characters, or I guess size of character. Like at this point we are not doing any decoding, so it's just the encoding. Output length, output I don't know. It's just C for you. Let's also check the lower index. Maybe I'm overwriting it somehow. But I'm not using output at anything else, just here. And it gets written to 0. Okay, that's kind of annoying. So literally you can see the index and the number, but then here it's 0. Oh my god, I have to be like that. I mean, I was right with it's probably because of the dereferencing, but I think you have to dereference and then index it. Like that's fucking annoying. Okay. Order of operations again. Like here I was cautious enough to use parentheses, but here I forgot about that shit with the star and indexing being like opposite orders. Okay, even here then I have to be careful. Like yeah, if you put parentheses, it's gonna dereference it first and then index it, but you know, you're not really expecting that. Okay, whatever. So we see the modified bytes, right? And if we just call decode. So decode works also by allocating memory, I would assume. Yeah, it also allocates memory. So let's say we want to decode our output. It has a length of output length, and we want our original message back. Let's do original and original length. So pointer original and original length. Okay, so let's show the original length. And maybe right, so it's 70. So here it changed it like that. Yeah, maybe I'll try to find a way to print these numbers in binary so we can actually see the code at the end. And let's think. Obviously actually checking for the errors and maybe correcting them. Maybe we need some kind of a way to randomize the data after it was encoded, like put some bit in there. I'll try to write that function on my own. But yeah, I don't think we have time to actually implement all of this today, so I mean we can continue next time. I don't think it's a problem. So yeah, but I mean the main part, just encoding the thing and being able to decode it, we still have to implement the actual checking for errors. But that would be that. So yeah, I guess that's it for today. Hopefully this was interesting. I guess here we can avoid that issue by doing that, but yeah, this was kind of annoying, honestly, with the parentheses, but it is what it is. And even here, I guess, I don't know why it doesn't like passing G like that. Maybe it wasn't about G, maybe here it was also because of that ordering. No, it is because of G. I don't know why. Yeah, whatever. So yeah, I guess that's gonna be it for today. And oh, so Hamming code is an error correction code. We went over like the explanation of how it works in the beginning, if you want to watch that. Like the intuition on how you get from just parity bits to the full Hamming code. So it lets you send data across the network and add some information about it so that you can actually fix errors that can occur in the bits. That's what it does. And wanted to use it for the stake tool, just just practicing basically. So yeah, that's gonna be all for today, and let's see in the next one. So until then, see you.